In science, the correct number of digits to use in recording physical quantities means that the last significant digit has physical meaning. This means that the error in the measured quantity is no more than about 1 to 3 units of the last digit. So today you're going to listen to me speak about and then complete some exercises about the number of significant figures and calculations with significant figures. The number of significant figures is significant because it tells us the accuracy of the measured quantity. If we were to get a 5-gram mass, an approximate mass, and we put it on a balance with an accuracy of, so it reads to 3 decimal places, 0.001 grams, then we would write, for example, this is just one example, that the mass was 5.046. We would not write 5.0 grams, and we couldn't be more accurate than that, 3 decimal places, so we couldn't write it as 3.04613 grams, for example. In values less than 1, so with a decimal place, the first non-zero digits, so the non-zero digits are not significant figures. So if the mass we wrote down we took the mass of 0.0054 grams, it has only 2 sig figures. The zeros in front of that are not significant figures. With decimal fractions, trailing zeros are used in science to denote the accuracy of the measurement. In maths, you probably usually delete them. So I've got an example of this. So if I measured a mass of something and it came up on the scale as 0.05 grams, it has an accuracy of about plus or minus 0.01 grams. Whereas if I measure something and I write down the mass as this, 0.0500, this tells me that it's more accurate because it's got an accuracy of 0.0001. This one only has 1 significant figure. This one has 3 significant figures, so more accurate. We can use scientific notation to try and avoid making incorrect calculations. So 1.5 by 10 to the power of 3, that tells us that there are only 2 significant figures in that calculation, whereas 1.500 by 10 to the power of 3 tell us that there are 4 significant figures. Here are some examples for you to work through. The answers are on some of the later slides, so you can have a look at that then. Same with these ones. These ones are to do with rounding and significant figures. Obviously, this will be important for your assignment so that you're rounding correctly according to the significant figures. So there are 2 rules for deciding the correct number of significant figures when we're adding and subtracting or multiplying and dividing. So the rule for when we're multiplying and dividing physical quantities, the number of significant quantities in the answer is the number of significant figures in the least accurate of the input numbers, so the least accurate of the input numbers. For example, if we needed to multiply 3.742 by 0.41, we would need to write the answer as 2 significant figures because this one, the least accurate one, only has 2 significant figures. So the answer would be 0.15, whereas if you type that into your calculator, it'll say 0.153422, which is not the correct number of significant figures. When we're adding and subtracting, the answer should have the same number of decimal places, not the significant figures, so same number decimal places as the least accurate input quantity. Once again, it's the least accurate. This is because the answer needs to imply the same accuracy as the least accurate input. So if I was measuring something, 4.1 centimeters, and I need to take away for some reason, and I measured it as, when I write my answer, I would only be able to go to one decimal place because that's what the least accurate input was. It doesn't matter how accurate this second quantity is, because the 4.1 is only plus or minus 0.1, meaning it only goes to one decimal place. We can't make the answer more accurate than the least accurate value. A lot of you will be using volumetric glassware, so pipettes, volumetric flasks, and burettes. Volumes of pipettes and volumetric flasks are often given without the correct number of significant figures because it's expected that readers know the accuracy of such instruments. So, for example, if we have a 25 milliliter pipette, which some of you might use, it has an accuracy of about plus or minus 0.1 milliliters. This gives us an average for, or the kind of accepted value for all volumetric measurements is an accuracy of about 0.5% to about 1%. So we need to assume 3 significant figures for pipettes, burettes, and volumetric flasks, even if less figures are given. So if I'm writing it as 25 milliliters, that's actually 25.0 milliliters, or 2.50 by 10 to the one. Here are some questions for you to do, and then the answers are on the next few slides, so I'll just click on them for a little while. You probably have to pause it though.